it is too small that now we will not be able to waste a lot of time going to the disk, then coming back. So if you can look at now the first come, first serve, what we were looking at, we were moving from one disk to the other, but we were doing what you call bypassing. So we are using a concept of what you call bypassing disks. And when you use a concept of bypassing disks, what we say there is more time wastage. So why can't we read the disks that are closest to the reading head? Then after that, we move up to the last disk that is the farthest from the reading head. So we want to make sure that now we can have efficient disk or efficient reader write of these disks, and we can be able to reduce the seek time that we have within the data presentation. So how can we do that? The only way we said we can be able to reduce this is by using what you call the shortest seek time. And if you can look at all algorithms that you have already worked with, you find that now seek time or shortest time is the best algorithm that you can use in the data presentation. So in this case, today I wanted us maybe to go to another algorithm that we call an elevator. And that algorithm, we call it a scan algorithm. And we will still use the same concept. Yes? Anybody?
There's one quiz you gave us.
Yes?
But our answers are not the same. So I don't know whether you can tell us how it is being done.
Oh, the question, I think from the time maybe I gave you, I had not gone back, but I can maybe trace it where it is. Let me trace it where it is.
Okay, then we do it.
Yes, then after that, maybe we can be able to do together.
Okay.
Before we go to the next algorithm.
Yeah.
So, just a minute. So I think I added some information from that question. Remember, the question was not clear. Then I added some information, and I think you got those information.
Yes.
So I will mark the question because if you have seen I have not marked that question. I'm sorry for that. So I will mark that question so that now we can be able to understand maybe what we were supposed to have. So if you look at the question that we had, the question reads, using the following queue, and maybe I can copy this queue. Using the following queue, calculate the total seek time using the following algorithm. The reading head is at 47, and the disk has 200 readers. So remember, maybe I can use Paint. That is the best one to use for now. Just a minute. Need to copy it, then we can see it. So that is the algorithm. That is the queue, where the first track is 56, the next one is 89, the next one is 2, the next one is 45, and the next one is 9032. We had 32? 232s?
Yes.
Oh, okay, there is no issue, but now that is a waste of a disk because we cannot have that 232. I'm sorry for that. Maybe we can give it to 39. So if it is that 232, the last disk was a waste. So you cannot have two disks of the same name or of the same type. So you must have disks of different types and different names. Maybe this one we can give it 34 or 35, given to that. So I think we can copy that again. Maybe we look at that as a question. And if you look at now the question, the reading head is at 0.47. The reading head is at 47, and there are 200 readers. Another name for a reader is what? I remember I gave out the presentation of a Sereda, and I said this Sereda can be presented in two ways. One is a Sereda, the next name is what? I'm waiting for an answer. If you won't mind. Sumaya, are you in class?
Yes.
Sumaya, are we together?
I am.
Okay. So, what is another name for a Sereda?
Well, I don't know, sir. I'm
Okay.
trying to listen, but I'm in a noisy place.
Okay. So another name that we said we can give to this Sereda, we said it is also called a track. If you can remember the diagram that we had previously, before the last week, that is last week but one class, we said a Sereda is a composition of various disks that we have within our hardware. And in this case, we are trying to read the disks. And when we are reading them, we must be very efficient when we are reading them. So in this case, we are using what we call the first come, first serve algorithm. And remember, in this, I'm avoiding programming, my friend. I don't want to do programming for now, because that is part of now structure. And at the moment we meet in structure, I will be able to program that.
Okay.
So for this case, if you look at this aspect, we said we cannot move from track 0, then we count all these tracks, because we said tracks are supposed to come from 0. Then the last disk is supposed to be 200. If you have started with 0, so automatically the last track should be 199. That is what we said. Because if you look at the question that we had, we said if a track has a position 0, then the last track, which is now 200, is supposed to be 200 minus 1. And we are supposed now to include all the tracks from 0 up to 199. But instead of including that, what we do, we just take the tracks that are in position. So we can take the first track, which is 2, and the next track, which is greater than 2, now we can give it to 32.
32.
Then we have 35.
Yeah.
Then from 35, we have 45.
Yeah.
Then 45, remember our reading head is at position number 47.
47.
So the next track that we're supposed to have is 56.
Then 89.
Then the last track that we're supposed to have is 89. Remember, our main aim is to read these tracks. At the moment we read these
90.
tracks, yes, is there any question?
There's also another track 90.
There is a track, okay.
90.
There is a track 90 here.
Yeah.
Maybe we can overwrite that. And here we have 199. Thanks for that. So these are the tracks that we're supposed to read. And when you're reading these tracks, the question that we're supposed to ask is, the moment I switch on my computer, do I waste time reading tracks because of one fault, mismatch, and miscalculations of the algorithms that we have? So in this case, we want to read this disk, servicing them as per the arrival time. Remember, we are using first come, first serve.
Yeah.
The first track that arrived in the queue is like when you go to a bank and you are the first person to be served. Automatically, we cannot serve the person who came maybe earlier or who came after you. So we have to serve the person who came earlier. So that is now the algorithm that we are using. And I remember I said most of the algorithms that we use them to assist us in creating an efficient transition from one point to another. So that we will not have what you call data emittance of some information that we have within the presentation. So in this case, if now our reading head is at position number 47, now what we need to do is to read the track that was the first one to arrive. And the first track that was the first one to arrive is 56.
Yeah.
So in this case, you form the first move. You form the first move. Then from 56, you move to 89.
Yeah.
You form the second move. Then from 89, we are supposed to move directly to 2. Remember, we are still servicing those tracks. So this becomes number 3. So automatically, there is waste of time, 1, because if you look at now, these are tracks that are from 89 to 2. We need to service 45, 35, and 32, but we have not serviced them. So automatically, we are doing away with speed, and then we are doing away with efficiency, which is one of the important factors that we need to consider. So in this case, we can now move from 2, then we move to 45.
Right.
Then when you move to 45, the next track that you're supposed to service is track number 90.
Yeah.
Then when you service track number 90, you service 32.
32.
Then the last track that you're supposed to service is now 35.
Right.
So automatically, we are forming a mismatch of executions. And this way that we are doing with this algorithm, sometimes you find it is not efficient and it is not the best algorithm to use because we waste a lot of time reading several disks. And that's why sometimes you find that most of the tracks, they have some faults. Either you are trying to read a track, but it cannot read because now we were using some undefined algorithms. And these undefined algorithms, one of them is what you call the first come, first serve. So if you can remember the notes, we said this is not the best algorithm to use. And one, it is not the best algorithm because of inefficiency. It is not the best algorithm that you can use because sometimes we are looking at now where these algorithms do what you call oscillation. So that's why we said there are some oscillations. And these oscillations are the ones that are reducing the speed, creating some defect of these tracks that we have. So that's why we said we can now move to shortest seek time. And according to our question, we were supposed to use those 2 algorithms. But before we go to those 2 algorithms, we need to calculate now what you call the average seek time. And the moment you are calculating the average seek time, the advantage of calculating the average seek time is now to calculate the efficiency. Remember, efficiency cannot be measured. You always have to measure efficiency through acting on a certain disk. So from this track to this track, how many tracks have you moved or have you passed through without servicing them? So that's why we say 56 minus 47,
Yeah.
Then we get what?
9.
9. So we are supposed to get 9 tracks that we have already bypassed. Then from 89 to 56, there are some tracks that we have already bypassed. Then you move up to where we have the last track, which is 35. Then when you add, you divide by the number of tracks. And the number of tracks that you are supposed to have are 1, 2, 3, 4, 5, 6, 7. So when you get that average, the average that you get, now it is equivalent to the combination of efficiency. So that's how we measure efficiency in these disks that we always have. But we cannot measure efficiency through looking. We measure through action or acting through the disks. So that's why we said this one has a lot of delay. And because it has a lot of delay, the seek time is very high. The average seek time is very high. And we moved to what you call the shortest seek time. Have I answered the first question?
Yeah. So the question was, you wanted us to calculate the total seek time. So you don't divide by the number of tracks.
Oh, okay. The question was calculate the total seek time. If you are calculating the total seek time, now we're not supposed to divide by 7.
Yeah.
Because that is not average,
Yeah.
So you can still get you can still get now which is the best algorithm by determining the minimal total seek time. Remember, the average seek time, we are calculating efficiency. But when you get the total seek time, what we get within the total seek time is now as a presentation of which algorithm is taking the smallest duration within the execution. So we can still measure which algorithm is the best in terms of speed. The best algorithm in terms of speed is the one that has the lowest total seek time. Are we getting that?
Yeah.
Yes, and Sumaya, are you in class still? You're not responding. Hope you are in class. You can still catch up. I think now you are somewhere you can now clear here.
I can hear you guys, but I have 5 kids here screaming around. I'm so sorry.
Okay, don't worry, don't worry. That is the nature of running at home, telecommuting.
No, it's only today I was asked to babysit them.
Oh, don't worry, don't worry. Don't beat them.
Sawa. That's why I'm muting.
Yes. Okay, there is no problem. So the next algorithm that we were supposed to look at is what you call the shortest seek time. And if you look at the shortest seek time, I want to use the same method. I think you have understood this. I want to do away with this method so that now we can move directly to that algorithm. And what we said, we need to make sure that now we are using the latency delay is too small and the waiting time is minimal, because we cannot do away with the waiting time. It is very hard for you to do away with waiting time. But we can now try to reduce the latency delay. So we need to improve the response time. That is our aim. Let us improve the response time. Let us improve the throughput, meaning we are improving the number of executions that we can execute within a given time. That is now visiting the disk or visiting the tracks. So in this case, if we are moving from 47, we have to compare 45. Remember, 45 is the next one that is closest to 47. 56 is the one that is closest to 47. So you have to compare the distance between 47 and 45 and the distance between 47 and 56. So when you get the difference between 47 and 45, you get the difference is 2. But here, the difference is what? Is that 8?
9.
Now, automatically, we cannot move to 56 because now the response time will reduce. But our main aim is to improve on a response time. I think you understand what is a response time at this time. The time that you take to respond to a certain event, which will be able to improve in the execution of a certain process. That is now what you call the throughput. Making sure that now we can be able to minimize the executions, maximize the executions, and minimize the waiting time. But the only way we can be able to minimize the waiting time is to make sure that now we visit the disks that are closest to the reading head. And when you look at the tracks that are closest, we have already said that the first one is 47.
Yeah.
So I want you to do calculation, and maybe next class you can tell me the difference of the total seek time. You tell me whether the total seek time is the same with these algorithms that we have. Then now the reading head is at this position. And because the reading head is at this position, so what we need to do is now to compare 45 and 35, then 45 and 56. So what's the difference between that 5 and 45? Is that 10?
Yes.
The difference is 10. What about 5 and 56? Is it 11?
Yes.
From 45 and 56, remember, we are now comparing. So this one becomes now the middle point or the access point. And because it is now the access point, we are now trying to do what you call access denial or access restriction on a given process that you can access. That is that too. We give the access denial or access restriction, but we pave way for the comparison of the tracks that have not been visited on the other side and on the other side. So if you look at now, it is at 45. Now you compare this 35 and 56. So automatically we get now the tracks, these are 11, 10, these ones are 11. So you move towards this track. When you move towards this track, you find that we are not even comparing, because from that 35 to 32 and from 35 to 56, now the distance is increasing. So automatically we move to 32, then we move to 2, then automatically we can move directly to 56, then we move to 89, then we move to 90. So in this response, what we can say is that we have tried to remove dependency in terms of delay. So we don't have delay. We have tried to improve in the execution. We have tried to increase in efficiency. And when you try to increase in efficiency, automatically we will be able to read more tracks at a given point. That's why when we are using a disk and you spin, maybe you are spinning as a CD, automatically you find it is running at a very high speed. That is almost equivalent to 10 decibels that we are supposed to execute within a given point. So within this time, we will be able to find that even if we have not calculated the total seek time, we will be able now to move from 47 to 45, then from 45 to 35, then from 35 to 32, then from 32 to 2, then from 2 to 56. Because for you to read 56, you must pass through from 2. Then from this up to this, from this up to this. So when you add all of those, you get now what you call the total seek time. Are we getting?
Yeah.
Is there any question up to that point? Remember, we are doing a recap on what we did last week, given that we had what we were supposed to do.
The shortest seek time first.
Pardon?
The shortest seek time first. Is it 2?
I'm not understanding your question, please.
What is the shortest seek time first?
Yeah.
Is it 2?
This one or what? The one that I am.
Yeah,
yes, this is 2. Remember, we are using this 2, eh?
Yeah.
Yes. Is that clear now?
I'm talking about the shortest seek time.
Yes.
So in the quiz, you said we calculate the shortest seek time first.
Yes, we calculate the total seek time first.
Shortest seek time first. You said shortest seek time first.
The algorithm.
Yeah. In the diagram, you said
according
you calculate the total seek time and the shortest seek time first.
I think I'm not getting your question. Let me write it somewhere. Maybe I understand.
Yeah.
So you are saying I said shortest.
We calculate the total seek time and the shortest seek time first.
The total seek time.
Yeah.
And
the shortest seek time first.
Was that the question?
Yes.
Let me check it. Maybe it had some issues there.
Yeah.
Oh, okay. If you look at the question,
Yeah.
calculate the total seek time.
Yes.
Calculate the total seek time using the following algorithm. First come, first serve. Shortest seek time first. So if I can elaborate clearly, we are supposed to do the total seek time for the first come, first serve algorithm and the total seek time for the shortest seek time first. Are you understanding that way?
Yeah.
Is it clear now? Is it easy for you to get the total seek time?
Shortest seek time?
Yeah?
What is the shortest seek time in the diagram?
I think you need to be clear. You are breaking somehow.
So what is the shortest seek time first in the diagram?
The one that I have already given you, this one.
Yeah.
This one. That is the shortest seek time first.
Okay.
Then the other one was for first come, first serve.
Yeah.
Can you remember the one that I have already rubbed?
Yes.
That one was
The
for
first
first
one
come,
I'm
first.
okay with.
Oh, you
The,
are okay.
yeah.
So for the
Literally the
shortest
second
seek
one.
time is this.
Yeah.
Can I repeat it again?
Yeah.
Yes.
Okay, let me repeat it again. So I'm using the same algorithm. I'm using the same queue. And for this queue, if you look at the shortest seek time, we are not following the arrival time. What we are following is the disk that is closest to the reading head. So if you look at now, according to our question, if I can go back to our question, the question was the following algorithm. The reading head is at 47 and the disk has 200 serialized. So for this case, our reading head is at 0.47. So if you're using the shortest seek time, you have to compare 47 and 56 because we can move in either way, either from left to right or right to left, or from this point to the right, or from this point to the left. So if now we assume we are moving to the left, if we assume we are moving to the left, we have to compare from 47 to from 45 to 47. Those are 2 tracks. See there?
Yeah.
Yes.
Then 47 to 56, these are what? 8 tracks. Now, for this case, we look at now, because we need to reduce completely the waiting time, and to improve on response time, our main aim is to make sure that now we can be able to move to the right, to the left side, because now it is the one that has few tracks. So you first of all visit the tracks. We go to the path that has the fewer tracks so that we can be able to visit them and write them or read them. Then after that, we can visit from that point. So in this case, that's why we said we can now say we are moving from 47 to 45. That is the first one.
Yeah.
Our reading head is at 0.45. So from 45, we can move to 35 or we can move to 56. Now you compare the tracks. So from this point, how many tracks are there? These are 10, see you?
Yeah.
From here up to here, these are 11.
11.
So if you look at now, these are more than these. So you move to the side that we have fewer tracks. Then when you compare, I remember I said there is no need of getting the difference from 35 to 56 and from 35 to 32, because you find that now we always say that when you move towards 32, we have fewer tracks. So we move to this side. Are we together?
Yeah.
Then maybe here this is where we had an issue. Maybe okay, here we had an issue. According to what I have seen, because we have to now look at now. This is a track that we have. The reading head is at position 32, and because it's at position 32, you compare this track and 56. How many tracks are there?
24.
24.
There are 24. Okay, I can see now, Joshua, why you are complaining on this, and I'm grateful for that. You are understanding. I can see now you are understanding what I'm saying.
Yeah.
Because if you look at now from 32 to 2, the difference is 30. So automatically we move towards 56. I'm sorry for that. We were supposed to move towards 56.
Yeah.
Are we okay now?
Yes.
Sumaya, are you okay now?
I'm fine. I'm fine.
Okay. So from 56 now, the reading head is at 0.56. So from 56 to 89 now, can you look at the tracks that are in between 56 and 89? How many tracks are there? So those
33.
are 33.
Yes.
Are they 33? Serious? What about
Yeah.
from 6 to 2?
54.
54. So automatically we move to this direction.
Yeah, 89.
Then we move to 90 automatically. Then we are supposed to move to what?
2.
2.
To 2. Now, what we can say is that we can conclude, because if you are given this model, we can come up with our own interpretation. And that's why I always say that it's good to understand before even you go to that exam room, because when you understand the diagram, you can interpret from that diagram. Well, we can say, if the tracks are farthest from the reading head, they create wastage of time. And that is why we have seen we are moving from 90 to 2. That is wastage of time. And because this is wastage of time, we are now trying to create some defection within the devices that we have. And that's why we find that most of the devices sometimes it cannot go for a long time. Maybe it is for 3 years, 2 years, according to the usage. Because now these tracks are reading the tracks, moving from left to right without reading the way they are supposed to read. So in this case, we can say this is the best algorithm than the first come first serve. And I think you'll prove that. Maybe we can prove. Let us prove. Let us prove. From 47 to 45, those are 2 tracks. Plus, from 45 to 35, those are 10. Then plus, from 35 to 32, those are 3. Plus, from 32 to 56, those are
24.
24.
Yeah.
Then from 56 to 89, those are 33.
33. Yeah.
Plus, from 89 is 1.
1.
Plus, from 90 to 2.
88.
Is it 88?
Yes.
Now, 88 plus 1, that is 89. 89,
Yeah.
That is 89 plus 57, because I have added 24 plus 33, plus 57. So this becomes 6, 14. Am I right? I'm not a mathematician, my friend.
Okay.
Yes. So from 2, that plus 2, that is 15, plus 15. So if you look at this, it's 11, 161. Am I right? Equals
Yes.
out. See in 161. So you can see now our total seek time is 161. Our total seek time. Total seek time. So suppose we go now to the first algorithm, which was first come, first serve. So I want you to maybe put this in mind that we have 161 in the shorter seek time, so that we can come up with what you call the first come, first serve. So we have 161 for the shorter seek time. I want us to get the clue on which algorithm is the best algorithm to use for now, if you are working with those 2 algorithms that we have. So allow me to draw so I can use this side, or maybe I can use, maybe let me use a rubber. I have some issues here. Maybe we start at this point, where we say we are starting from 47. From 47, then the first one was 56, then 89, then we had 2, then we had 45, then from 45 we had 90, then from 90 we had 32, then from 32 we had 35.
Yeah.
So can we do these calculations? From 47 to 56, is that 8?
9.
9.
Oh, okay, 9. That's why I'm saying I'm not a mathematician.
We are also not.
From 56 to 89?
33.
33.
33. From 89 to 2?
87.
87. From 2 to 45?
43.
43.
From 45 to 90?
45.
45.
From 90 to 32?
58.
That is 58.
Yeah.
From 32 to 35, that is
3.
3.
Yeah.
Now let us do these calculations. 9 plus 33, that is 42.
It should be 278.
Yeah?
Total is 278.
I had 78.
278.
Oh, the total.
Total, yeah.
278, eh?
Yes.
So we are getting 278, and the next one was 161, eh?
Yeah.
Now, which is the best algorithm to use for now?
Shortest seek time.
Yes, because it has the least seek time.
Yeah.
Or the least seek time. Are we together?
Yes.
Yes. Any question up to that point? Maybe you can ask questions before we proceed to the next algorithm, because I know we have understood now.
Yeah.
Is there any question?
No.
No,
And
okay.
this is examinable in NEC. The last question was in year 2016. So I'm expecting the last question in certificate was in 2016. So I'm expecting a question from this, either in July for those people who are doing exam on July, and for those people who are doing exam on November, I'm expecting it.
Okay.
So can we move to the shortest, to the scan algorithm?
Yeah.
So when you use the scan algorithm, we say that it's like an elevator. Do you know what is an elevator?
Lift.
Yes, lift. Now I want to ask a very simple question here. Suppose I have a building of 56, or maybe I have a building of 10, maybe stairs within that, or maybe buildings or rooms.
Yeah.
So when I move the first stair or the first floor, maybe we have 10 floor. We have 10 floors. When we move to the first floor, the second up to the 10. Suppose maybe there is a person who was coming from ground floor, that is at 0, and was moving to 10th floor and presses up to 10th floor. So when this person presses up to 10th floor, and within the time, there is nobody who has already pressed the lift, so automatically it moves directly to number 10.
Yes.
Yes.
That, does it go back to 0, or does it retain its status at floor number 10? Where does it go if nobody has pressed the key?
It stays there.
It stays there.
Yes,
So
unless somebody presses.
the elevator method is the one that works best in this presentation of servicing the disks that are closest to the reading head. Then after you service the disks that are closest to the reading head, then you can move to those tracks that are farthest from the reading head. But in this case, there are some things that we need to understand. And one thing that you're supposed to understand when you're using the scan, because I will be using the same algorithm, the same queue, sorry. Allow me to use the same queue. And maybe I can do away with this for now. Maybe allow me to do away with this so that I can explain. So if you look at this, what we are saying is, if you are using the scan algorithm or the elevator method, what we do, we move to the tracks that are closest. Then after that, you surface the tracks that are farthest. You either look at now from where the reading head is, how many tracks am I supposed to pass through to go to point number 0 or to go to point number 199? Now, that is now the calculation that you're supposed to do. When you're moving from 47, when you're starting from 47, sorry, you have to look at now, which direction am I supposed to follow? When I'm following that direction, how many tracks am I supposed to pass? If you look at from 47 to 0, we have 32, we have 2, 35, and we have 45. So we have 2, we have 45, we have 32, and we have 35. But if you want to move towards 199, we have only 2 tracks. Now, in this case, we can visit the tracks that are more fast on a given direction. Then we can be able to pass now to the tracks that are fewer afterwards. One, we need to improve in access. So in this case, we move from 47, then it must have what you call a turning point. We read the track that is closest, which is 45, then 35, then 32, then 2, but we must have a turning point, which is called head 1. So we are turning point, we are having a turning point, and we go back to the track that are fewer on the other side. So we move to 89, then we move to 90. So in this case, if you look at this algorithm, what comes in our mind is that we must have a turning point. If our direction was on this side, and we are moving on this side, we must have a turning point at 199.
99, yeah.
Then we start reading the tracks that are closest, which is now 45, then
Yeah.
that. But for now, because now we are looking at the tracks that are more, we can first of all service that. The next thing that we're supposed to look at in this algorithm, because we have that freedom, we need to look at now, suppose the reading head was at point 2. And now we are supposed to look at those tracks that are more on this side and tracks that are fewer on this side or more on this side. We find that we don't have any track that is supposed to be read on this side.
Yeah.
So automatically, we cannot start reading the tracks on this side. We must move here. We have a turning point.
Yeah.
If the reading head is closest to 0, first of all, move to 0. If the reading head is closest to the end, which is 199, first of all, move to that. But if the track is farthest, you have to compare how many tracks do we have from 0 to that point where we have the reading head. And from 47, maybe, or from the reading head to the end of that track, so that we can be able to see which direction are we supposed to use. Are we getting that scenario?
Yeah.
Are we getting?
Yes.
So I want to give you 2 minutes. You ask a question. I want to give you 2 minutes. You ask questions. I take a glass of water so that I can come back. Am I allowed?
Okay. You're allowed. Zumaya,
Yes, Joshua.
last week sikuelewa hii shortest sick time, but saizi nimeielewa.
Boy, oh boy. Mimi itachukua time kiasi. I have to go back and read. Then come back and revise.
Hujaielewa bado?
Nimeelewa somewhat.
Oh,
I'm following, but kind of sijaelewa.
but saizi mimi at least niko sawa. Hii first come first serve na nilielewa siku ya kwanza. Sasa shortest sick time ndio sikuelewa vizuri. Hata sikujua diagram zinachorwa mbili. Mimi nilichora diagram moja kwa ile quiz.
You make time, alafu we revise together.
Okay. Mimi hata nani kumbe Sayanka alielewa vizuri siku ya kwanza. Je, alikuwa ananiuliza tunachora diagrams ngapi?
Hujampigia? Why is he not in class?
Ana bundles.
Alafu, what about the other units? Zile entrepreneurship.
Imagine
Eh,
mwalimu wa communication skills alikuwa anafunza leo from 8:30.
why?
Sasa nashangaa kwani timetable sisi tulipewa wrong. Juu yeye alikuwa anafunza tena watu walikuwa watu 6. Ni venye sikuingia. Niliona tu
Why is she
moderator.
teaching lakini? See, we have a timetable.
What I want us to look at is what you call the scan algorithm. So already we have done first come, first serve, shortest. Now we can look at scan algorithm. And we are saying it is elevator. Is it elevator or elevator?
Elevator.
Elevator, I think something like that. If I'm not wrong, elevator.
Yeah.
Elevator. So if you look at the elevator method, we are saying it is the same as what you call the scan algorithm. But in this case, we're looking at now visiting the tracks that are closest to the reading head or that are more in the leading head, that are more on the. So you first of all pass the tracks that are more, then you pass the tracks that are fewer. And that is why if you look at now in our own interpretation here, because I want you to use this presentation here, we are saying we move from 47, but if you're moving to 10, we must have a turning point.
Turning point, yeah.
But remember, it depends with the question, and that's why I want you to go to your question papers. I think you have question papers, eh?
Yeah.
Do you have
Yeah.
question papers?
Some, but I can
Some.
go.
So can you go and look at those question papers? You see whether there are some questions about these algorithms. So what we are looking at, sometimes we can be told, if now the tracks or maybe the reading head moves towards 199, towards the last track. If you are told that the track moves towards the last track, automatically we cannot move to 10. So we move towards this, serious.
Yeah.
Then the last track that we are supposed to visit is 2. So we are not moving 2. So we only have one head. We only have one head. And this head that we have here, which we are calling head 1, now this one is a wastage of time. It's like we are having a wastage of time. So that's why we say it is a bit flexible, but there is a wastage of time because of this algorithm that we have here. Just a minute.
Okay.
So I think, Joshua, now we can continue. Joshua, I think now we can continue.
Yeah.
Okay. I'm sorry for disturbance. So if you look at this algorithm, and I will not follow these diagrams that we have here. Remember, we said that this diagram has been mixed, so we are not following these diagrams that are here. That's why I'm following my own diagrams that we have already drawn. So if you look at this question, automatically now we need to calculate what you call the total sick time. And for you to calculate the total sick time, now you need to consider the aspect of maybe calculating the time. Let me try to calculate. So from 47 to 45, how many tracks are there? So you find that now there are 2 tracks.
Yeah.
10 tracks. From 45 to 35, those are 10. Then from 35 to 32, those are 3.
Yeah.
From 32, that is 30. So if you try to add these are 33, 43, 45.
Yeah.
So 45, then 45 plus from 0 to 56, you add that. So plus 56. So which becomes 11, 101. Then from 56 to 89, how many tracks are there?
From
the 56 to 89, because now we are here.
33.
From 56 to 89.
33.
33. Is that 3?
Yeah.
So that is 134. Then from 89 to 90, that is 1. So it becomes what? 135. So if you compare this algorithm and the other algorithm, which was having 161, 2 something, and this one is 135, we can see we are now trying to reduce the wastage of time. And when you're reducing the wastage of time, we are trying to come up with efficiency in the tracks that we have. And that's why we can look at this point where we are saying the tracks that we have here, they are able now to improve the executions. So we are now improving the execution. So the throughput increases. The throughput increases. Whereas now, if you look at the others, we were trying to improve on response time, to reduce on response time, whereas we are supposed to increase on response time. So in this, we can say the first algorithm that we can use is the scan algorithm. The next algorithm is the shortest seek time. And the next algorithm is what you call the fast come, fast what? Yeah. So automatically, maybe we can say this is using
I have a question on the diagram.
Yes?
I have a question on that diagram you have just, yeah.
This one,
So
okay.
from 2 to turning point, you don't subtract that
From 2
to the turning point.
Oh, from 2 to turning point. So you have 2 minus 0. I'm sorry for that. Those becomes that 7. And that 7.
Okay.
Is that okay now?
Yeah.
Yeah, that is 137. I think it's because it's clumsy. That's why we have some issues with calculations.
Okay.
So 137 for the first come, first server. This one is resulting to is it to that something or to that
278.
278?
Yeah.
Then for shorter seek time, this one is
161.
to
161.
161.
Yeah.
So if you look at this, this is the best algorithm for now. And that. So if you can conclude with this, we can say when you are using the scan algorithm, we service the tracks that are closest to the reading head, and then we must have a turning point to those tracks.
Yeah.
So let's go back to our notes. If you look at this algorithm that we have, we are saying we are moving from 50, we move to 34, we move to 11, then we have a turning point at what? 0. Then we move towards the next direct or towards the left right direction. So in this case, we can say those tracks that are farthest from the reading head will result to what you call starvation. So in this track, there is starvation.
Yeah.
But in this, we don't have no what? No starvation. Because when you are the first one to arrive, you will be the first one to be executed. So we don't have starvation. But for the first one, we have starvation.
Yeah.
Are we getting now?
Yeah.
So are we getting
allow me to copy the diagram?
What?
Allow me to copy the diagram.
At the
For an elevator.
For elevator?
Yeah. I just
So
want
we
to
can
know.
say there's a diagram that we can pull it here. Just a minute.
No, not this one. The one you are painting.
Okay, let me come. This one, huh?
Yeah.
Yes.
I want to note it down.
Okay, you can. Is that clear? Can you see it?
Yes, I'm seeing.
From 47 to 45 to 35 to 32 to 2, then we have a turning point at 0. Then after that, we move to 56, then to 89, then to 90.
Yeah.
Have you noted it somewhere? So after you note it, you can tell me.
Okay. Just 2 minutes. 2 minutes. I'll be done.
Okay. Okay.
Yeah.
Are you through?
Yeah.
Okay, so we can continue. So have you understood? Are you?
Yeah.
Are you okay with this?
Yeah.
Okay, so we can continue with the next one. And I want to go to, remember we said we have C-scan, we have scan, and then we have what you call the circular scan. The circular scan. So in the circular scan, it is the same as the scan algorithm. But when you look at this, we must have a turning point on both ends. So it's like we are having two heads.
Okay.
So in this case, if you look at this, so what we can do, maybe allow me to use another, maybe I use the same, so allow me to use the same page. Allow me to use the same page. Or we can maybe use this page. Allow me to go to another page. So in this algorithm, if you are starting from 0, so we said we start from 0, then from 0 we have 2, then from 2 you have that 2, then from that 2 you have 35, then from that 5 you have 45, then you have 47, then from 47 you have what? 56.
Yeah. 89.
Then we have 89.
9.
Then we have 90.
90, yeah.
Then the last one is
199.
or 99. So
Yeah.
we are assuming those are, I think those diagrams are still clear.
Yeah.
And see those diagrams. That. So if you look at this, we are saying, if you are visiting these tracks, either you must move towards 199 and you must end up at 0. So in this case, the first question that you're supposed to ask yourself, for you to improve on response time and to improve in execution, we can count how many tracks are we supposed to visit from 47 to 0. Those are about 46. Then from 47 to 199, how many tracks are we supposed to visit?
130.
So you find that now it is like 199 minus 147. You find that now we have a lot of tracks that we are supposed to visit.
Yeah.
So automatically we move to 10 now. We visit this, that, and then we have a head. So in this circular scan, we are now supposed to move towards the last track, 199. Then you start visiting the tracks that are closer to 199. And then we have 156. Can you see the difference between a scan and a C-scan? In a C-scan, we are moving to 10, then we visit the tracks that are closest to now 0, or that were not visited from 0. But for this case, we are visiting the tracks up to 0. Then after that, you go through the tracks without visiting them, up to the last track, then you start visiting them one by one. So in this case, we can say it is like we are moving from 199 track to 0, which now always results to 199, which results to 199. So in this case, we can say our total seek time is 199. Our total seek time is 199. Because what we do, we move from 47, we see whether it will result to 199 or less than, because it's not supposed to be more than. So from 47 to 45, these are 2 tracks. From 45 to 35, those are how many tracks? 10.
Yeah.
From 35 to 2, how many? 32, that is 3.
33
tracks. That becomes 15. 15 plus now 30, that is 45. 45 plus 2, that becomes 47. I think we are okay, Sirio?
Yeah.
Then from 199 to 90, how many tracks are there? From 199 to 90, you get we have 9, then we have 109
Yeah.
plus 47. This becomes what? 16, 5, 1. Then from 90 to 89, that is one track,
Yeah.
which becomes 157. Then from 89 to 56, how many tracks are there?
33.
Those are 33. So this becomes 190. So I have said it must be less or equal to, but it is not supposed to be greater than 199. So that's why I'm saying if you're using the C-scan algorithm, there is no need of calculating all these calculations that we have here. We can take 199 minus 0, and then we are able now to get what? The total seek time. Are you getting that?
Yes.
So if you look at this, we have two hands. So this is now head 2. And because we have two hands, there is a lot of wastage of time. But now we can say this is the best algorithm than the first come, first serve algorithm. Are we getting that? So we still see that the first come, first serve algorithm is the worst algorithm that we can use in the development of this structure or the model that we have. But the first one is the scan, the second one is the shortest, the next one is what? The circular scan.
Yeah.
Are you getting that?
Yeah.
Any question up to that point? Maybe you can have a clarification, maybe a question. If you don't have a question, maybe we can go to Luke algorithm.
Yeah. So I'm okay.
You're okay? Sumaya in? Ama amepotea?
Ameniambia bundles zimeisha.
Oh, sorry. I'm sorry for that. We understand, We understand.
Yeah.
So for this case now, we can understand that when you're using this algorithm, we are wasting a lot of time, but it is still the best algorithm than other algorithm like first come, first serve. Let's try to look at now the look algorithm. And there is one thing that I want us maybe to see it here, where we always say that when you're using look algorithm is the same as scan algorithm. It is the same. The only difference that we have within the look algorithm is that we are not supposed to visit 0 or the last track. We visit the tracks that are supposed to be visited. Let me use an example. If I use the same example here, the same diagram here, let me use the same diagram here. If you are moving from 47, so we move towards 45, towards 35, towards 32, towards 2. But for this case, we are not visiting at 0. Now, we visit the track that was not visited on the other end. Are you getting that?
Yeah.
So we are moving towards 0, but we are not visiting 0. But now we try to visit the tracks that were not visited. And when you try to visit that, you'll find now the algorithm. Like now here we are getting what? This is 2. This is 10. This is what?
3.
Yeah? 3. And this is 30. What about this? 56 minus 2?
54.
54.
Yeah.
Then from here we have 30.
33.
Then from here we have 1.
Yeah.
So if you try to add this is 12, 15, 45. That is 99. Is it 99?
Yeah.
Plus that. Remember this is 54. So this becomes 3, 11, 12. Can you see that?
Yeah.
The total seek time for this now becomes 123. Can you see that now we are trying to reduce completely the wastage of time, and we are trying to improve on the response time, and we are still trying to improve on the executions. Now, if now we are trying to reduce this completely, we are now creating more efficiency. And when you understand about efficiency, we are looking at this is a system that can be able to work within the defined or with the defined systems or defined hardware or software that we are using. So at this point, we can see this becomes the first algorithm, this becomes the second algorithm, this becomes the third algorithm, this becomes the fourth algorithm, and this becomes the last algorithm. Are we getting that?
Yeah.
If I'm too fast, you can tell me.
So
Am I?
no.
So we can still continue. So
Yeah.
that's why we are saying, if you look at the notes, I don't want to use this, these diagrams. I don't want to use these diagrams. I think now you can be able to understand the diagrams and you position where they are supposed to be. Yeah? We are saying in a circular scan, just like the elevator, to some extent, it begins to scan towards the nearest end and it works away with that. So this is now the one that you are supposed to carry it to this point. So for this case, we find that this is the best algorithm that you can have on that. But now we can look at now the next one that we have already looked at, which is, so this one can be a C-scan. We will see how is it a C-scan. So for the look, do we have a look? Okay, we don't have a look here, but we can add to our notes. We can add to our
scan.
Yes?
Is it called look scan?
Yes, look scan. It is called look scan. So this one is called look scan. And when you're using look scan, it is like when you are burning a CD. When you're burning a CD, you go through the tracks. Then after that, you come and service those tracks. But you're not moving outside the tracks that are not supposed to be serviced. We are moving towards the tracks that are supposed to be serviced, then you start servicing them one by one. The next one is what you call the circular scan, or the circular look. So circular look, so this one we have said, it is the same as the scan algorithm. And I think we have seen the difference, because the difference is where this one is moving towards 0, but this one is not moving towards 0.
Yeah.
So this is look algorithm. So this one is moving to, it is not moving to, it is not ending at 0, but this one is turning at 0.0. But when you look at this, it is the same as the C-scan. It is the same as the C-scan. And if you look at the C-scan, we are moving towards 0, towards the end. But for this case, we are not moving towards 0, and our case is supposed to be like this. Allow me to use the same presentation.
Yeah.
Allow me to use the same presentation. And we are moving from this disk. We move to this. We move to that 5. We move to that 2. Then we move to 2. Then we are not supposed to move to 0. We move to the last track, which is 90.
Yeah.
Remember, that is our last track that we have within the queue. Then after that, we move towards 89. Then we move towards 56. Can you see that?
Yeah.
Now, what we can look at here is that we are now moving this, which becomes 2. This becomes 10. This becomes 3. This becomes 30. And this becomes what? So we are reading this. We are not interested with this because we are not servicing it. What we are interested with is 90. And this becomes 1. And this becomes what? 36. That becomes 33.
Okay.
So that's 34. 34 plus 12, 15 plus 45. So this becomes 79. So in our case, we can see this has what you call 79. So we can say that is efficient. And we can also say that the response time is high. The response time is high. And still, we can be able to say we have less waiting time. We have less waiting time in the execution. Are we together?
Yeah.
Yes. Now you can ask a question. I can wait for any question that we have, because that is the end of those algorithms that you're supposed to cover.
So circular scan is almost the same to circular look. The
But
way
circular,
they need
which one?
circular look and
Yeah.
circular scan are almost the same.
Circular
Only
look at
Only
scan.
that circular scan has a turning point.
We have for the circular scan, we are moving 2 and 0 and the last track, serious.
Yeah.
But for this one, we are diverting 0.
Yeah.
We are diverting this and we are diverting this.
Okay.
Yes. Any question?
No question.
So I think maybe you can go and maybe try to attempt a question. Maybe that I will be able to post here, and we see whether maybe you can be able to answer that question.
Okay.
I want us to get the definition or the differences between all the algorithms that we have already talked about, so that now we can, maybe after you complete, we'll be able to have a chat room. Maybe we can chat. And then maybe next time, you can start maybe from another topic. And please, what I can urge you, please, tell your friends, come to class. Tell your friends to come to class. Because for any class, it is good to communicate. If there is an issue with the network, please, they need to communicate. Because I don't want to assume that maybe there is maybe it is ignorance. I don't want to assume that is ignorance, maybe if you're not attending the class. Because I can see there are some few people who are attending class. But make sure that you tell them to attend classes, because it is good. Remember that we are doing this as a normal class. Remember, I am teaching the way I can teach in class. And I will be able to follow all the steps that are supposed to be followed in discussion. Is that true? Is that okay?
Yeah.
Is that okay?
Yeah. But we have a problem with the common units.
Which common units?
Like communication skills and entrepreneurship.
What is the issue?
They don't follow the timetable. I think they're teaching at the wrong time.
At what time? Maybe we can confirm that. Just a minute. Just a minute. Let me try to set this exam, and then usiende kwanza, sidio?
Okay.
So that now, when I set this exam, I will be able to show you the timetable, sidio?
Yeah.
Then we see whether there is an issue. If there is an issue, I will communicate to the HOD.
Yeah,
So don't.
Two units. We have a problem in 2 units.
Yeah. Which and which?
Entrepreneurship and communication skills. You have never been taught.
Entrepreneurship, and who is supposed to teach you entrepreneurship?
Mr. Nicholas Osir.
Mr. Nicholas Osir.
Yeah.
Is that an let us go to the timetable. Let's see whether maybe in the timetable we can see it. Just a minute.
Yeah.